Quantum computers, you've heard the hype, right? They're supposed to be these miracle machines promising to solve problems that our best supercomputers couldn't crack in 1,000 years. We're talking about creating life-saving new medicines, maybe even completely revolutionizing finance. But here's the thing. There's a huge hidden catch, a massive problem we don't talk about enough. These things are absolute power hogs. So let's get into it. Let's explore quantum's fascinating power paradox. So, okay, what exactly is it that gives these machines this almost mythical power? Well, it all comes down to completely rethinking the most fundamental building block of all information. Okay, so think about the device you're watching this on right now. Your phone, your laptop, it all runs on what we call classical bits. And they're pretty simple, right? A bit is either a 0 or it's a 1. That's it. But a quantum bit or a qubit is a totally different beast. It's an absolute game changer. Because of this wild principle in quantum physics called superposition, a qubit can be a 0, it can be a 1, or, and this is the mind-bending part, it can be both at the exact same time. That right there, that's the secret sauce.
And what does that secret sauce actually get you? Well, look at this number, 1024. Here's what that means. A regular computer works one step at a time, linearly. But a quantum computer with just only 10 qubits, can check out all 1024 possibilities at the exact same time, simultaneously. Their power just explodes exponentially, and that's what lets them even think about tackling problems that are completely, utterly out of reach for any normal computer.
Yeah, it sounds incredible, almost too good to be true. And, well, that's because unlocking that insane power means we have to face a challenge that is just as massive. And I mean that, quite literally. The challenge is chilling. So, what is the catch? Well, it turns out that these quantum states, this whole being a 0 and a 1 at the same time thing, they are ridiculously fragile. I mean, unbelievably delicate. The tiniest little vibration, the smallest change in temperature, and poof, the quantum state is gone, wiped out. So the big question becomes, how in the world do you protect something that fragile? You have to get them cold. And I don't just mean put it in the fridge cold. I mean absurdly, mind-bogglingly cold. The leading quantum computers today, the ones that use what are called superconducting qubits, have to run at just a tiny, tiny fraction of a degree above absolute 0, the coldest temperature theoretically possible in the universe. And just to put that into perspective for you, the empty, freezing vacuum of deep space, yeah, that's practically a beach vacation compared to this. So why? Why go to such extreme lengths? It's because any heat at all, any thermal energy, it basically makes the qubits jiggle. And that jiggling completely wreaks havoc, destroying their special quantum state. The process is called decoherence, and it just obliterates the information. Gone. So what kind of machine can even do this? It's called a dilution refrigerator, and you can basically think of it as the most powerful, most complicated, and yeah, most energy-hungry refrigerator ever conceived. It's not just cooling the processor, it's literally the life support system that keeps the whole thing alive. And as you can probably guess, all of that extreme cooling comes with a very, very steep price. We're talking about energy. Just one of these quantum computer systems, really just its life support, can burn through the same amount of electricity as like 20 to 40 regular houses, all at once. And that's not just for a moment. That's a huge constant power draw, 24/7. And when you actually break down where all that power is going, you find the real paradox at the heart of all this. The quantum processor itself, the qubits that are doing all the magical, incredible calculations, they use a tiny, minuscule fraction of 1% of the power. It's almost nothing. Meanwhile, a massive 80% of all that energy is going into just one single job, keeping the thing cold. So this really sums it up perfectly. The quantum magic, the part that does the work, it's actually super efficient. It's all the normal, classical machinery we have to build around it that's the real energy guzzler. So you see, cracking this infrastructure problem, that's the real key. That's what's going to unlock the future of quantum computing. But okay, it's not all doom and gloom. Here's the really good news. This enormous challenge has basically lit a fire under the entire community. It's kicked off this amazing race with scientists and engineers all over the world trying to figure out how to make these things radically more efficient. And one of the first things you realize is that, well, not all quantum computers are created equal.
The most common ones right now, the superconducting types, are the really power-hungry ones we've been talking about. But there are these other, totally new approaches popping up. You've got neutral atom computers, for example, which are already proving to be up to 10 times more energy efficient. That's a huge leap. And then there's the holy grail, photonic quantum computers. These use particles of light, and they have the potential to work at room temperature. Think about that. No more giant energy-sucking refrigerators at all.
And hey, even for the super cold computers, people are coming up with some seriously clever innovations. They're working on things like new amplifiers that create basically zero heat. They're figuring out how to move the control systems inside the fridge itself, which cuts down on the heat leaking in. And they're even developing brand new refrigerators that don't need super rare liquid helium to work. I mean, it's just brilliant stuff. And look, this isn't some far-off science fiction dream. We're talking about seeing real game changers, like those zero-heat amplifiers, maybe as soon as 2026. That's right around the corner. In fact, a lot of researchers are predicting we'll hit this energy efficiency inflection point within the next 5 to 10 years, a moment where things really start to change. Of course, the ultimate goal, the big prize, is to develop totally new kinds of qubits, like these things called topological qubits, that are just naturally stable enough to work without all that crazy cooling. So, okay, after all this, you have to stand back and ask the big fundamental question, right? With this massive power problem, is it all worth it? And that brings us to the ultimate trade-off.
But just when you think you have it figured out, there's a really surprising twist in the story. Get this. For all of that energy they need for cooling, a modern quantum computer actually uses way, way less power than a top-of-the-line classical supercomputer. I'm talking about a beast like the Frontier supercomputer, which can burn through something like 1,000 times more electricity in a single day. It's not even close. So what does that tell us? It tells us we're not really comparing apples to apples here. The real metric, the thing we should actually be looking at, isn't the total power used per day. It's the energy it costs to get a solution. And for the very specific, incredibly complex problems that only a quantum computer has a prayer of solving, they might actually be the most energy-efficient way to get the answer by far. And this is where we get to the most incredible, kind of beautiful paradox of this whole story. It turns out that the exact kinds of problems that quantum computers are uniquely good at solving are some of our biggest energy and climate challenges. We're talking about things like designing a super-efficient power grid, discovering brand new materials for better batteries, or developing next-generation solar cells. Think about that. We might need a power-hungry machine to solve our planet's power problems. Which really leaves us with one final critical question to think about. Let's say, down the road, a quantum computer helps us discover some new material that completely revolutionizes renewable energy. When that happens, are we even going to care about the electricity it took to power that computer? Will we even remember it? That right there, that's the multi-billion-dollar bet that companies and governments all over the world are making as we speak.